Welcome to another explainer. Today, we are literally shattering the textbook illusion of a flat solar system. Seriously, if you've ever looked at a diagram of our cosmic neighborhood, you've almost certainly seen this neat, perfectly flat disk of planets just circling the sun like a vinyl record. But what happens if we throw that two-dimensional map entirely out the window? Today, we're taking a cosmic elevator straight up and down into the 3D universe to discover the mind-bending structures that exist far above and far below our planetary plane.
Okay, let's just dive right into this by questioning those familiar models we all grew up with. Yes, the bulk of the objects in our solar system do orbit on this same general plane. And this happens mainly because of angular momentum. As the ancient cloud of gas and dust spun and collapsed to form our sun and planets, it naturally flattened out into a disk, kind of like tossing pizza dough. But that simple 2D plane is just a tiny fraction of the whole story. Space is profoundly, massively three-dimensional. So what actually exists above and below us?
Here is our flight plan for today. We'll start with the 2D illusion. Fly through the zodiacal dust cloud. Brave the chaotic scattered disk. Check in on the Voyagers in the heliosphere. Plunge into the spherical Oort cloud. And finally, float out into our interstellar neighborhood.
Part 1. The 2D's Solar System Illusion. Let's establish our baseline.
Before we go up or down, we need to know where the floor is, right? So the crucial point here is understanding the difference between the ecliptic plane and the galactic plane. The ecliptic plane is essentially the flat plane of Earth's orbit around the Sun. Most of our major planets closely follow this invisible saucer in space. However, our entire solar system is also tilted relative to the much larger galactic plane, which is the immense disk of the Milky Way galaxy where most of its mass actually lives. Establishing this baseline is absolutely essential because up and down in space are completely relative to these planes. And honestly, we immediately break this flat illusion by just looking at some of the oddballs right in our own backyard. Take the dwarf planet Pluto. Instead of behaving and staying perfectly flat on the ecliptic plane like the major planets, Pluto has this steep orbital inclination of about 17 degrees relative to the rest of the solar system. When it orbits, it's actually plunging far below and rising way above the paths of those 8 major planets.
Moving on to part 2, the zodiacal dust cloud.
If we look just slightly above and below the planets, things get a bit dusty. We find this massive 3D inclination of a symmetric dust cloud extending well off our flat planetary axis. This is known as the zodiacal dust cloud. It's this ever-present veil of tiny solid particles, silicates, ices, and minerals. Basically, it's a messy remnant from the formation of the planets, fueled by ongoing collisions between comets and asteroids. And fun fact, this diffuse cloud is actually a huge headache for spaceborne observatories. The dust scatters sunlight and creates this bright infrared background that can completely obscure deep space observations. Part 3. The chaotic scattered disk. Welcome to the wild, icy highway.
As we travel further out from the Sun, we start seeing a massive contrast between two completely different populations of icy worlds. On one hand, you have the classical Kuiper belt, sometimes called cubanos, which generally behave themselves on near-circular, relatively flat orbits. But on the other hand, you have the wild, scattered disk. Because these objects come just close enough to feel Neptune's gravity, they get violently scattered. Neptune acts like a gravitational bully, knocking these bodies into extreme, highly eccentric orbits that can be inclined up to 40 degrees off the ecliptic. They are literally being launched high above and deep below the rest of the solar system.
Part 4. Voyagers and the heliosphere.
This is quite possibly one of the most mind-bending facts about our actual cosmic exploration. We didn't just send our space probes straight out along the flat plane. Not at all. Voyager 1 is currently rising at a steep 35 degrees above the ecliptic plane, traveling at over 320 million miles a year. Meanwhile, Voyager 2 is diving downward at an incredible 48 degrees below the plane. They are acting as our ultimate cosmic elevator operators, proving that humanity's exploration of space is fiercely, undeniably three-dimensional.
Now, surrounding these probes and all of our planets is something called the heliosphere. And again, this isn't some flat ring, it is a massive, protective 3D bubble created by the solar wind, which is the stream of electrically charged gas blowing outward from the sun in literally all directions. Eventually, this outward wind crashes into interstellar gases and abruptly slows down. This edge, which scientists call the termination shock, happens everywhere around us, in a giant sphere between 80 and 100 astronomical units out. And just for context, 1 astronomical unit is the distance from the Earth to the Sun, so it's huge.
Part 5. The spherical Oort cloud. The absolute outer boundary.
1.6 light years. I just want you to let that staggering number sink in for a second. This incredibly vast distance represents the outer edge of the Oort cloud. Unlike the flat disk of the planets we're so used to seeing, the Oort cloud is a giant, extremely thick spherical shell of icy space debris. We're talking about chunks of ice and rocks, some bigger than actual mountains, that completely engulf our planetary plane in all 3 dimensions. It extends from about 5,000 astronomical units away to a massive 100,000 astronomical units. So when a comet suddenly plunges toward Earth from straight up or straight down, it's actually falling right out of this massive spherical deep freeze.
Finally, Part 6, our local interstellar neighborhood.
To understand where we are right now is truly mind-bending. Our entire solar system is currently moving through something called the local interstellar cloud, which astronomers affectionately call the local fluff. It's roughly 30 light-years across. But here is the crazy part. The temperature of this cloud is about 7,000 Kelvin. That is nearly the temperature of the Sun's surface. Now, you might be wondering, why aren't we burning up? Well, its density is incredibly low. We're talking just 0.3 atoms per cubic centimeter. To put that into perspective, Earth's atmosphere, even at the very edge of space, has about 12 trillion molecules per cubic centimeter. So if you were to stand on Earth right now, totally ignore the tilted ecliptic plane of our planets and look straight up and straight down, perfectly perpendicular to the wider disk of the Milky Way galaxy itself, what would you actually see? Well, your eyes would point toward the galactic North Pole and the constellation Coma Berenices, and the galactic South Pole toward the constellation Sculptor. You'd literally be looking straight out of our galaxy, peering directly into the deep intergalactic void. From the tilted, quirky orbit of Pluto to the deep-diving path of Voyager 2, all the way out to the spherical, mountain-filled shell of the Oort cloud, space is profoundly, wonderfully 3-dimensional. It's so much more than a flat diagram in a textbook. We're going to leave you with this final thought to spark your curiosity. Knowing what's above and below us, how does this 3D perspective change your view of Earth's cosmic voyage? Thank you so much for joining us for this explainer, and remember, always keep looking up and down